Okay, here we are still in chapter 18, about midway now, third lecture in, and we're going to continue to talk about amines and amides, and just like the previous two lectures, we'll actually be continuing to focus on those amines. The focus for this particular lecture is heterocyclic amines. So far we've talked about how to deal with an amine when it's part of a chain or coming off a benzene ring. Now we're going to look at an amine when it's actually part of a ring. That hetero means something other than a carbon in the cycle, in the ring itself. So heterocyclic, we already dealt with this with the hemiacetals and acetals having that oxygen in the ring. Now we're going to look at what happens when we have a nitrogen in the ring. So obviously a heterocyclic amine is a cyclic organic compound, and they have a 5 or 6 atom numbered ring, and they contain 1 or more nitrogen atoms in order to be a heterocyclic amine. So we see a few there. There's pyrrolidine, pyrrole, imidazole, piperidine. Pyridine is a very common one as an organic solvent because it looks similar to benzene, but it does have that lone pair on the nitrogen. And then we have pyrimidine and purine, and those are going to be very important when we talk about our DNA and proteins, as we discuss those two particular types of groups. So you'll see more of these in later chapters, but we'll start to introduce the concept of heterocyclic amines here and now. Okay, so there we have it. The purine and pyrimidine rings are found in DNA and RNA. I think I might have said DNA and proteins. Obviously, DNA and RNA code for protein synthesis, but it's the DNA and RNA that I meant to mention as being the purine and pyrimidine ring containing compounds. We'll also see heterocyclic amines like piperidine are found in black pepper, so not a source you might expect, but again, a natural source of this particular heterocyclic amine. And with 2 or 3 double bonds, they have aromatic properties similar to benzene. In particular, I mentioned that pyridine is used as an organic solvent similar to benzene, but it can do things that benzene can't. So that lone pair on the nitrogen, for instance, can interact with metal centers and do interesting things that benzene itself could not do. When you replace one of those carbon atoms with a nitrogen, suddenly you still have an aromatic ring, but you have new and different properties possible. Okay, so let's see how closely you were paying attention to those heterocyclic amines. So here we have 3 different heterocyclic amines. This learning check asks you to identify them. Go ahead, pause the video if you need to, flip back if you really need to, but these are pretty common and you're going to see them. So hopefully if you haven't committed them to memory, you'll do so soon. Good luck. There's our piperidine. Again, maybe knowing that it's in pepper, it looks a little bit like pepper, the way we spell it. At least it's got the 2 P's, right? So that might help you remember that one. It's got all single bonds, so it's going to be a sort of ring that has bends to it. It's not going to be a flat planar substance like pyridine or benzene. If we look at B, now we're down to a 5-membered ring. So 6-membered ring with piperidine, 5-membered ring is pyrrolidine, and then finally once we form some double bonds there and get something that's similar to an aromatic, we get pyrrole. So hopefully you have committed those 3 structure types to memory, and obviously that slide that had the 7 main heterocyclic amines, they should all be pretty much committed to memory by the end of this chapter. So I don't ask you to memorize much, but especially since we're going to see the purine and pyrimidine rings as part of the RNA and DNA structures, please do try to commit those 7 heterocyclic amines to memory shortly. We mentioned earlier in this chapter that we'll often see nitrogen amine functionalities in drugs, and alkaloids in particular are physiologically active nitrogen-containing compounds. They're produced by plants. They can be used as stimulants, anesthetics, antidepressants. Unfortunately, they're often habit-forming, So it's not a great thing if you can avoid these, like nicotine that we see here is an alkaloid, and it certainly has its addiction properties. So hopefully you've never tried cigarettes and never do. If unfortunately you've tried them and become addicted to that nicotine, it's quite a difficult thing to stop, and hopefully it's a habit that with some help you can stop if you need to stop. But there's nicotine, a natural alkaloid, and conaine is another alkaloid. And again, the commonality is that you have nitrogen containing, in these cases, nitrogen rings. So that's why we're talking about them as heterocyclic amines. Here's another alkaloid, caffeine, and again, it's not quite as damaging as nicotine, but it's quite addictive, and certainly many of us have this addiction. It's a stimulant of the central nervous system. A lot of people can't start their day without their daily dose of caffeine because of those stimulant properties. It's found in coffee beans, tea, chocolate, soft drinks, colas in particular, and it contains an imidazole ring. So that's one of our heterocyclic amines, and that's why we show that in the caffeine structure to the far right, as well as some people enjoying their beans, and then finally a young woman enjoying a nice cup of coffee. Following up with some other alkaloids, we have alkaloids like morphine and codeine that are produced by the poppy and therefore have been used for centuries as painkillers, opium wars, and things like that around the poppy plant as a result of those psychoactive, bioactive alkaloids. There have been modifications to morphine to give us things like heroin and codeine. Again, the codeine occurs naturally in lesser amounts in the poppy, but can be made synthetically and is often part of a prescription cough syrup. You'll see codeine as one of the painkillers if you have a really severe dry cough that's causing a lot of pain. It's often provided there. It's not nearly as addictive as morphine or heroin, but it does provide some pain relief there. So there we have it. Unfortunately, of course, there's the heroin epidemic in our area nationwide, and it's one that's a very sad story because it seems like medicine. It's often for people who have abused prescription opiates, and then they move on to heroin addiction as an illegal narcotic. But like I said, it's tough because these are effective painkillers, and people tend to be in severe pain who abuse them, and so it's a very sad situation. So let's talk about pharmacology. As I said, I know a number of you are interested in the health professions, nursing in particular, and so you'll probably take a short course in pharmacology itself. But for those who might not otherwise see much pharmacology, we'll take just a moment here to talk about pharmacology, which is the study of drugs and the development of new drugs. And so some main areas of pharmacology research are to design drugs such as procaine, lidocaine, demerol, that retain some of those pain-killing properties of the alkaloids, but in order to minimize the addictive side effects, the structures have been modified. So cocaine and morphine have been modified to produce anesthesias that do not have those addictive side effects, or at least minimize the addictive side effects. Morphine, there's nothing like it. We haven't been able to create anything that's as effective in terms of killing pain. Morphine's still prescribed to people who unfortunately probably won't need to come off of it because they're stage 4 cancer patients or other people with severe diseases that are not likely to get any better. So they're given it as a pain relief medicine because we don't have anything that will relieve pain to the level that morphine does. But obviously it's an addictive drug, and like I said, it tends to be reserved for those hospice patients, end-of-life patients that we don't need to worry about the addiction because unfortunately they won't live very long or long enough to need to come off the drug. And so here you see that cocaine structure. We've seen it earlier in this chapter, and we see how it's chemically modified to give procaine, where we sort of break up that heterocyclic amine ring, fused rings actually, to give something that's straight chain type of tertiary amine, and then lidocaine is a similar structure with some methyl groups on that benzene type ring later on. And so those have been developments in pharmacology that have decreased the addiction. Unfortunately, they're not as effective at killing the pain, but they do a decent job with the pain without the addictive side effects. Okay, so before we leave this lecture on chapter 18, let's have one last learning check. So here we're asked to identify the heterocyclic amine in serotonin. So this is the structure of serotonin, and if you would go ahead and pause the video here if you need a few minutes to identify that amine, try to recall it from memory, or like I said, as you're still learning as we go along, peeking is okay, but by, say, test time, you should hopefully have the 7 major heterocyclic amines from that earlier slide committed to memory. So good luck. Okay, so this one was tricky because you have the 2 fused rings, but only one was heterocyclic. And so the heterocyclic amine was that 5-membered ring that is a pyrrole. So hopefully you were able to identify that and recall that from memory. If not, you've got a little while, like I said, to commit those to memory. And certainly by the time we hit the last chapter on nucleic acids, we hope you'll at least have the purines and pyrimidines memorized. If you are continuing to struggle with any of these concepts from this lecture or any of the other lectures in Chapter 18, please do reach out to me for help. Otherwise, I will see you in the next lecture.